Hey everybody, Mr. Troy here. I got a great video for you today about taking zeros and turning them into equations. It's time for math with Mr. Troy. Okay, so the idea here is that we are going to take some information and turn it into a function or an equation that satisfies that information. Some of this should make a ton of sense to you already because of the work that we've done. Okay, so let's take a look at it. Find a fourth degree polynomial function in standard form with real coefficients that has -1, +1, and 3i as zeros. Well, the fact that it's a fourth degree polynomial tells us that it has to have 4 zeros. And the fact that it has real coefficients gives us this nice conditional statement that if 3i is a 0, then -3i is also a 0. Okay, so every 0 can be turned into a factor by writing it as x minus the 0. In practice, it is totally okay if you want to just write this as x plus 1 and x plus 3i. That's fine. Okay, now we have what we think is an acceptable polynomial function, but it does tell us that we have to multiply out into standard form. So I'm going to do that for each of these. Because of the whole difference of squares pattern, this is going to be x squared minus 1. And the same thing is going to work here. We're going to get x squared minus 9i squared, which is x squared plus 9. Then we're going to multiply those together, and this is going to feel like doing quadratic type. And we're going to get x to the 4th. The outers and the inners are going to combine to plus 8x squared. And the lasts are going to multiply to minus 9. So that is an expression. If we want to write it out as a polynomial function, we can say f of x equals x to the 4th plus 8x squared minus 9. Okay, next one's a little bit more challenging. Find a fourth degree polynomial in standard form with integer coefficients that has 2, 1/2, and √5 as zeros. So if I want to have rational coefficients, I need to find a way to cancel out this √5. So I'm going to have to use a negative √5 as well, for almost the exact same reason as this. So if you go to write that, you would say, all right, x minus 2, x minus 1/2, x minus √5, and x plus √5. But when you go to multiply that, you're going to get x squared minus 5/2 x plus 1 times x squared minus 5. So there are two ways that you can deal with this. Either you can just multiply everything inside of the first set of parentheses by 2, which you're allowed to do because you were making up the equation. It will still keep the same solutions if you just multiply everything by 2. So one way you could do that is you could say 2x squared minus 5x plus 2 times x squared minus 5. The other way is, instead of using x minus 1/2 when you started, you could use 2x minus 1. It has the same 0, but it won't give you a fraction coefficient. In any case, you will end up with this. And when you multiply that out, you get 2x to the 4th minus 5x cubed minus 8x squared plus 25x minus 10. So I want to use this next slide to illustrate how that process is pretty much just the reverse of what we've been doing for the last week. So for the last week, we've been taking some polynomial function, and we've been using different strategies to break it down as far as possible. Now, one of the strategies that we've used has been the rational roots test, the P over Q thing. We want to use that as little as possible, though, because it's time-consuming, and it kind of like melts your brain a little. You get really into, well, I tried negative 2/3, did I try negative 2/5? And so on and so forth. So, some things to remember. You still know how to factor by grouping. So if you can find a way to factor by grouping, your life is going to be a lot easier. Things that are written in even groups, so 4 4 terms or 6 terms, are things that are functions that are written in groups of 4 terms or 6 terms are often easier to factor by grouping. There are some tips and tricks you can use to factor things with odd-numbered terms by grouping. Anyways, I'm going to get x squared plus 5 times x plus 2. Makes sense that I would have 2 zeros here and 1 0 there. These are going to be different zeros. So you can start by saying x squared plus 5 equals 0, and x squared equals negative 5, and x equals plus or minus the square root of negative 5, which is x equals plus or minus root 5i. But it's a lot easier to just think of this as a difference of squares. The constant term is positive, so that would only work if it was imaginary. And the square root of 5 is root 5. So this is going to factor to x plus root 5i times x minus root 5i. And then don't forget the other factor that you've already listed, x plus 2. And that's going to give you these 3 zeros. Plus or minus root 5i and negative 2. So see how that's kind of the backwards process of going from a 0 to a factored equation to an entirely multiplied out function. Okay, so we're just doing the same stuff we've been doing before. We are just doing it in reverse. All right, this is our, I think, second to last example. Write the polynomial function in intercept form and then in standard form. Okay, so I see these 3 zeros, x minus 5, x minus 1, and x minus 3. Or, I see the zeros of 1/2, 1, and 3, and I write them in like this. So, sorry, that was a 0.5. Okay, if I go to multiply all of that out, let's just say ahead of time that I'm going to try doing 2x minus 1 and see what happens, because it might just work out that I need to do that anyways. it's not a bad way to start. I always like to FOIL out the back two first. I don't know why, I think looks nicer to me. And then I'm going to go ahead and I'm going to multiply this binomial times this trinomial. Okay, one benefit of being at home and always being on our computers is that we can always go to Desmos to check our work. And what you would notice if you typed this answer into Desmos is that its y-intercept would be -3, and that's not what I see here at all. Let's see what would happen if we plugged in, say, x equals 2 to our equation. So whenever I need to plug something in, I'm going to use synthetic division because it's a lot easier. Here the quotient won't matter. Although there certainly is something interesting about that 0 there. I get a -3. -3. What I really want is a +6. So in both of these cases, I wanted 6. And in both of these cases, I got -3. Well, what could we do to our equation to make it so that it has the same zeros, but has these points at +6 instead of -3? Well, we could multiply everything, every coefficient, by -2. So our answer for this one is going to be -4x cubed plus 18x squared minus 20x plus 6. And if we were going to write that in intercept form, we would just multiply this -2 in front. Okay, so you might be saying to yourself, okay, so we can just multiply stuff by 2 now and that's fine. Sure, because it'll keep the zeros the same. Because 0 times -2 is still 0. It will change every other point though. And finally, our last thing here. Find all the zeros of the following function. So one approach that you might want to take is graphing the function. Now, since we haven't done graphs yet, that's next lesson, one thing that you can do is you can go plug it into Desmos. So I see that I have a 0 at x equals 2, 2 comma 0. So if I go to synthetic division, x cubed, no x squareds, no x's, -8, and I plug in +2, let's see why that gives me a 0 first. I get this quotient of x squared plus 2x plus 4. Which means that since this would give us a factor of x minus 2, is that the original function could factor to this. Now, why don't I see any more zeros? Well, it's because this doesn't have any real zeros. So there, just like there's a difference of squares pattern, there is a sum and difference of cubes pattern. A sum of cubes works, but a sum of squares doesn't. We'll have to take a look at that. So go ahead and write these two factoring patterns down, and then we will take it from there when I see you next. Hang in there. Have a good one. Oh, right. End screen, so that I can have my total watch time percentage be lower, but so that the little end screen elements, like there's probably one here and maybe there's one over here, so that they don't like get in the way of what I was actually trying to teach.